This episode of The Energy Show is proudly sponsored by Sunlight and Power, the Bay Area's leading commercial and residential solar contractor. SLP has been designing and installing photovoltaic, battery backup, and solar thermal solutions since 1976. Help fight climate change. Go solar with Sunlight and Power today.
So, you want to save the world with clean energy? Make money doing it? Confused about the economic and technical realities of residential and commercial solar, batteries, heat pumps, EVs? Want the real-world scoop on new energy technologies, not manufacturer hype? Then tune in to the Weekly Energy Show, hosted by Barry Cinnamon. Insights from Barry's 40-plus years in the solar and energy industry will help you understand the future ways we'll generate and consume energy. And now, here's Barry.
Welcome to this week's Energy Show. Now, what's the best way for homes and businesses to get the energy they need? Now, think about energy distribution, not generation. In the 21st century, the cost of energy depends on where that energy is generated. I see four basic energy distribution options to get the energy from where it's generated to where it's needed. First, pipes carrying natural gas for combustion. Second, wires carrying electricity, a remote power plant, whether it's gas, solar, nuclear, wind, geothermal, whatever. Underground pipes for thermal energy capture in shallow trenches for heat pumps or deep wells for hot fluid and steam capture. And photons, just falling from the sky and captured by photovoltaic panels. Now, it turns out that for customers, energy delivery is more expensive than energy generation. Basically, it costs more to distribute the energy than to generate it. In essence, where the energy is generated determines how expensive it is. That means that rooftop solar PV is by far the least expensive, and that's borne out when we look at the costs. This has huge implications for the energy transition. So let's dive into each of these energy distribution methods. All right, we're going to kind of crank the history thing way back. First a bit. Humans learned how to build fires. Early heating for tents, for lean-tos, for caves, for houses, for cottages. Early heating was from chopping wood. Now, camping is fun for a few days, but it's really a chore to chop a few cords of wood to stay warm all winter. After wood, we had coal. Now, there's this discovery that this black rock called coal could also be burned and releases a lot of heat. But it wasn't until about 1885 that coal surpassed wood as the main fuel in the U.S. And that coal energy was delivered to buildings by horse-drawn carts. See old pictures of that. In the 1920s, fuel oil started to replace coal in building heating systems. There were coal-fired steam boilers. Those coal boilers were converted to oil heat. So they took out, the little basket where the coal was being combusted and they put in an oil burner. And then that oil was delivered by truck to a tank in basements, sometimes outdoors underground. That's what my family had in the early 60s. All right. Now, methane, also known as natural gas, heating took off in the 50s as the gas pipeline networks expanded through the U.S. Homes were converted from oil to natural gas. So we went from wood to coal, to oil, to natural gas. And natural gas has been the most popular fuel for urban and suburban heating since then, until recently, when heat pumps became popular. So with that history out of the way, let's talk about pipes, wires, underground, and photovoltaics. So almost every city and town has networks of underground natural gas pipes. That natural gas is used for heating and cooking, and it's all delivered from pressurized pipes. Now, sometimes people have propane tanks. That's if you're farther away and there's no natural gas pipes going there. You have a big propane tank sitting somewhere in the yard, and that propane tank is then filled up from a truck that delivers the propane. But these natural gas pipes in suburbs and cities, they've been underground for 75 years or more. Sometimes they leak, and they blow up, explode. Like the PG&E fire in San Bruno, it was caused by inadequate maintenance. Actually, the utility lost the records of where and when they installed the underground pipes. And there were leaks, but they couldn't figure out what was really going on until the leaks got so bad and they caught fire and a whole neighborhood was destroyed. So while we're on the topic of pipes, there's this old concept of heating buildings with networks of underground steam pipes. It's called a district heating system. So basically, you had a centralized steam boiler sending out steam in pipes, high pressure steam in pipes, And then the condensate, as the steam condensed in the radiators or in the buildings that were using it, it was pumped back and then it was turned into steam again. Now, sometimes these systems also had a centralized cooling provision where there were pipes sending out cold water from chillers for air conditioning, returning back warm water to be rechilled. So you had 4 pipes. You had the steam going out, you had this condensate coming back, you had really cold water going out, and you had warmer water coming back for air conditioning. So this district heating and cooling, I mean, it worked at college campuses. Actually, one of my first jobs was replacing leaking steam pipes at a Washington, D.C. college campus. And while I was at a college at this technical university in Cambridge, we used to go on steam tunnel hikes and kind of walk around and check everything out underground. Can't do that anymore. All the doors are locked and we weren't able to open them. Anyway, so this district heating was a pretty good idea last century. Not so good this century. Too much digging, too many pipes, too much maintenance, too much coordination, separate piping network for cooling. And you still need to heat the water with natural gas. Well, we're not going to use wood, coal, or oil. And you're not going to be able to heat water to that degree using photovoltaics. So it's not clean. And utilities like to build and maintain this underground, expensive energy infrastructure. Now, we have to take a step back and say, gee, wouldn't an air-to-air heat pump in every room or every series of buildings be much more cost-effective? Yes, air-to-air heat pumps, way more cost-effective. Not even close. But the utilities don't make money on those air-to-air heat pumps, and they're looking at ways of kind of building these district heating and cooling systems again. And in fact, I'm recently seeing some articles about utility-sponsored district heating and cooling concepts. There's even one kind of being talked about in San Jose. Not even close to being economically feasible compared to rooftop solar or utility solar and air-to-air heat pumps. You got to remember that when you're talking about district heating, that works great, but you can't get cold air to air condition out of those heating pipes. So you basically need twice as much equipment to do heating and cooling that most areas need. It's a step 100 years backwards. So this district heating concept is being promoted now by utilities trying to extend their natural gas monopoly and trying to extend their maintenance and the profit that they make on this underground infrastructure. Stick a fork in this stupid idea right now. It's not going to pencil out. So here's the thing about pipes. You have to bury the pipes. There's a huge underground piping network, and pumping fluids or steam through the pipes requires pumps, requires valves, requires lots of moving parts, separate tanks, things like that. It requires a lot of maintenance to ensure the pipes don't leak and burn down neighborhoods or just stop working. And this is expensive forever. This is a big maintenance nightmare. So kind of take a step back, and it's this really geeky from a high level standpoint. I make distinction between matter and energy. Matter is when you're moving things, objects, fluids, molecules, atoms around. That's matter. And thermodynamically, moving matter is a lot of work. The work is a thermodynamic concept. To move all that stuff, it takes work, whether it's just a therm of gas or a lot of hot water that you're using for district heating, or just pumping materials around. That's all because it takes energy to move that gas or move that liquid from point A to point B, which takes a lot of infrastructure and more energy. So when you're moving matter, it's expensive from a work standpoint. On the other hand, just sending energy by wire doesn't require moving any matter. It's just electrons. Electrons are kind of technically not matter. There's no work involved in moving an electron except for a tiny amount of electrical resistance in the wires. Very, very elegant. Very, very 21st century. And you can move a tremendous amount of energy just on thin wires with no maintenance. I mean, you just look at how much energy you're able to move power lines compared to the amount of energy you need to move in big natural gas pipes. With moving electrons, there's no moving parts. Much more reliable, much better than pipes. But you still need to move that electrical energy to buildings where it's used, i.e. you need to have wires going from where the energy is generated to the buildings that are using it. So you still need to install a lot of equipment. Things like high voltage utility transmission lines with towers. Now, sometimes we're talking about putting those underground, but it's even way more expensive. And then in addition to the long distance transmission lines, you need local distribution substations and transformers to convert the really high voltage on those high power lines down to the voltages that are used within a community. And all these distribution systems, these transmission lines, they need land for the transmission and distribution, and they're going to need a lot of maintenance. Okay, so we talked about moving energy with pipes versus moving energy with wires. Now, what about local energy? And this is kind of a cool concept that, it's something that initially makes sense. Geothermal. It's literally all Greek to me, earth and heat. So there's two types of geothermal energy. There's large centralized geothermal plants, and they started out in areas that are volcanically active. There's some systems like that run by PG&E in Northern California. You don't have to dig that far down. You get really hot water or steam from relatively shallow wells because there's like a volcano underneath. It's right near where there's molten lava. So then you can use that steam that comes out of the ground or convert the hot water into steam to run turbines and generate electricity. So it's a power plant, but you don't have to pay for the natural gas or the oil to generate that steam. The steam just comes out of the ground. But it still takes a lot of moving parts. And it turns out that the water and the steam, it becomes very corrosive. I learned that when I was doing these district heating systems. The condensate from steam is somewhat corrosive. But so you're able to get relatively free high temperature heat once you dig down far enough. Now, PG&E's plant in Northern California, it's pretty close to the surface, but maybe you go down farther, half a mile or a mile with a really deep well, you can get something really hot. But the power plant that's above those wells still needs to be generating electricity. And once that electricity is generated, you still need to transmit that electricity to cities. So even though the heating is free because you're getting it from a geothermal area, you still have the transmission cost of doing it, and then you also have the moving parts to maintain. So in the case of these geothermal systems, the energy is not generated locally. It's generated from a remote power plant. You still need those wires. So there's a new type of deep well geothermal. Now, they're coming up with the idea of, hey, let's drill a well really deep anywhere. I mean, you go down deep enough anywhere, you're going to get hot rocks. And, they learned this from the oil industry. When you're pumping oil out of the ground or natural gas out of the ground, you get a lot of hot water or hot oil or hot gas. And then from that well, you can build a steam power plant, and the steam is generated from heat from the well. This is all at a very early stage. It's got some potential, but you're going to have to dig really deeply. And the life cycle economics are really not known yet. You still need lots of moving parts. As I mentioned, the water and the steam is very corrosive. So I don't think the economics are going to be really, really that great, especially when you compare to the economics that you can get from a utility scale farm. You still have to transmit that electricity. Now, the second type of geothermal energy has been around for a long time. Typically what you'll have is a network of pipes that are buried 4 to 6 feet deep. And what happens is once you get about 5 feet underground, the temperature of the earth down there is about the same. It's like around 55 degrees, maybe a little bit cooler in northern areas and a little warmer in southern areas, but it's kind of stabilizes because the earth's always emitting heat from the central core and it's kind of going up, and the temperature at the surface depends on the air temperature, but the temperature 5 feet down is really kind of fixed. So you can capture that warmish heat from the ground. And what you can do is you can circulate a heat exchange fluid in these pipes. So you have trenches that are, let's call them 5 feet deep, and you're running a fluid through those trenches, and that fluid is always going to be at kind of like 55 degrees. So you can pull some heat out of that to cool the water down, the fluid down. Or you can, if you're running it in reverse in a heat pump, for air conditioning, you'd actually heat that water up, and then you would cool it by going into the ground. And it works, but in order to get the temperatures you need for the building, so if you're trying to heat the building, you're going to need warm air blowing into the building at 80, 90, 100 degrees. So you have a water-to-air heat pump system, pretty common, and then you turn that in reverse, and you can actually get some cold air coming off of that heat pump, just like an air-to-air heat pump, but the thermal source is really these underground heat exchangers. So it's kind of cool, literally cool and hot, but here's the problem with geothermal. Drilling these really deep wells in the first kind of that we were talking about, or digging the trenches around your house, it's expensive to do. You need pipes and controls. There may be leaks down the road. And you still need a heat pump to generate the correct temperature air for heating. As I said, it's like 90 or 100 degrees, and for cooling. So at the end of the day, you've got equipment in the building that's almost identical to an air-to-air heat pump. But then you have all the extra expenses for wells or trenches and pumps. And I have personal experience with this because I got fired from one of my first jobs after college because I was doing R&D work on a ground source heat pump system. We were drilling wells, 100, 200, 500 feet deep to get down to a constant temperature in an aquifer. And when I'm doing all the analysis, looking at the numbers and looking at the performance of the system, I realize, the cost of drilling the wells and installing the heat exchanger in the ground outweighed the efficiency savings. And what I learned back in the early 80s is even more true now because air-to-air heat pumps are so efficient, so cheap, so widely available. And it costs a lot of money to drill wells. And sometimes you don't know how much, what you're going to encounter when you start drilling wells or when you're digging a trench all around the house. So the numbers aren't going to work out as well for these geothermal systems, at least in homes, compared to an air-to-air heat pump. So that takes us to the last option for getting energy. That's what catches what falls from the sky. It's a photovoltaic system that converts photons in sunlight into electricity. Solar panels are dirt cheap. Manufacturing capacity is enormous. We're cranking them out. There's no doubt, nobody argues that solar is not now the cheapest way to generate electricity, by far and away. We have two flavors of solar power systems. We have utility scale solar and we have rooftop solar. By the way, both of them now are often equipped with batteries so you can get power at night. So utility scale solar, huge solar arrays, big power plants, 10 megawatts, 75 acres. Some of them are even bigger than that. Way bigger than that. Very inexpensive to build on a per watt basis. It's just mass production on a massive scale. Less than 2 cents a kilowatt hour, life cycle cost, including batteries. So you can generate the power really, really inexpensively, in the desert, or across the other side of the state, unoccupied land, 500 or 1,000 miles away. But then it's very expensive to build the transmission lines, and it takes 10 plus years to get those lines built. So you get the power from those cheap utility solar power plants to the buildings and the homes that need it. So, at the end of the day, that energy is generated remotely and great, but it's moved very efficiently on wires, but it costs a fortune and it takes a long time to put those wires up. So that kind of brings us to the most reasonable option. Reasonable from two perspectives. It's rooftop solars, although rooftop solar is more expensive to build. Yeah, a small rooftop power plant, 8 kilowatts, or a larger commercial system on a commercial roof like here in San Jose might be 250 kilowatts. Typically, the life cycle cost of those power plants, rooftop solar plants, are 8 to 10 cents per kilowatt hour with batteries. So it might be, 4 or 5 times more expensive to build those power plants than utility scale solar. But two really big advantages that we really need to think about. First, very fast to build these rooftop solar power plants because you don't need to worry about the transmission lines, typically 6 months. And it ends up being very cost effective because you don't have all the costs with running the wires from that distant utility solar power plant to the building that needs it. And, from a financial standpoint, the cost for these rooftop solar plants is paid by the building owner because they're the ones that are going to benefit from the power, not by ratepayers. So when you're looking at utility scale solar, although it's cheaper to build, it takes a long time. It's very expensive to get the right of way and run those utility wires, hundreds of miles. And the cost of all that work is paid by ratepayers and raises rates. So to wrap up, energy delivery from pipes is expensive. It's high maintenance, and it takes 10 or more years to build. And a lot of times what's going through those pipes is polluting fossil fuels. Energy delivery by wires is expensive for the transmission system and takes 10 or more years to build. Energy delivery from the ground is expensive for the wells and trenches if you're doing it locally, and it's also expensive for the wires if it's done remotely. But energy delivery from catching photons is dirt cheap, but only if the solar panels are on or near the buildings using the power. So, kind of wrapping up, the costs for energy depend on two criteria. First, where the energy is extracted and generated. If the energy is extracted or generated remotely, far away from the buildings or the homes that are being used, it's going to be expensive. Second, energy cost depends on who owns or sells the energy. If a business is selling you that energy, whether it's an oil and gas company, whether it's a utility, whether it's a geothermal power plant, whether it's somebody delivering propane to your home or your business, if a business is selling you that energy, it's always going to be more expensive than if you generate that energy yourself. Bottom line, rooftop solar is the cheapest energy source. It's also the fastest to implement, but it doesn't lead to profits of the incumbent energy providers who are fighting tooth and claw to avoid that cheap source of energy. Okay, That's all the time we have on this week's Energy Show. Thanks to all of our listeners for tuning in. And if you missed any of today's show, you can always go to the Energy Show website at energyshow.biz and listen to the podcasts.
This episode of The Energy Show was proudly sponsored by Sunlight and Power, the Bay Area's leading commercial and residential solar contractor. SLP has been designing and installing photovoltaic, battery backup, and solar thermal solutions since 1976. Help fight climate change. Go solar with Sunlight and Power today.